Welcome back. In this video, we're going to talk about the component form of the cross product in R3. As a quick review, remember that the main goal of lesson 4 is to develop the cross product operation. As we talked about in the previous video, the cross product as an operation maps two vectors in R3. The thing on the left-hand side of the cross product is a vector. The thing on the right-hand side is a cross product into a vector in R3. Notice this is not an X, it's a times symbol. It's a times symbol, and it's differently interpreted than this times symbol. This times symbol is a placeholder. This is a cross product between vectors. In order to develop the cross product, we're going to go back to the main uses of the cross product. Recall the cross product between two vectors in R3. Perhaps we call those two vectors x and y. So perhaps we say two vectors x and y in R3. We will write this cross product as x, and then I like to write the little times symbol a little smaller in between than I write my vectors, just so that there's no way that I'm confusing this with a letter x. So this is how we write the cross product. And we said that it will be used to do two things. Produce a vector, which we just named this vector. Remember, this thing is a new vector that is orthogonal to both x and y. It's a pretty powerful thing to be able to compress x and y into a single vector orthogonal to both of them. And then the second thing it's going to be used to do is measure the perpendicularity between x and y, where perpendicularity means the state of being non-parallel. We're going to start with this purpose to develop the component form, to get into the construction of the component form. We start here. All right, ready? We want to find a way to measure perpendicularity between vectors in R3 based on the cross product. So here was the concept. We had x cross y, and we want somehow, when we define this thing, we want to encode a measurement of perpendicularity. Just to introduce some ideas, I want to call this thing the first argument of the cross product. and I want to call this thing the second argument of the cross product. And you'll see why I do this later in this video and also in future videos. Okay. This is kind of hard to do in R3 to start with because R3 has 3 different components for each vector. One of the things that I'm going to suggest is let's study a similar, easier problem. This is a classic mathematician's game. You have a hard problem that you don't really know much about. Create a related, easier problem, solve that one, and then figure out what intuition you can transfer to the harder problem. So the related problem is, suppose you have 2 vectors, x and y, but instead of these vectors being in R3, suppose they're instead in R2. How might we measure perpendicularity? What does that even mean? How can we quantify a degree, some sort of a really, really perpendicular or not at all perpendicular, of perpendicularness? And I can't help myself. For those of you people that love grammar, you should sue me. Perpendicularness. The state of being perpendicular. The reason that I do this is because I want to start to build intuition. All of this is about intuition in many, many ways. Okay, so let's look at some cases. So here's some ideas that we might have. So if you have 2 vectors in R3, so most perpendicular. What would it mean to be the most perpendicular? When are 2 vectors the most perpendicular? Well, perhaps we say that the first vector is at 90 degrees to the second vector. So you would hope that in this situation, this is what we would want to be the most perpendicular, right? So this means a large number in the measurement, biggest measurement. So when we think about how to measure perpendicular, we want the biggest measurement. Okay. We could say that a vector is less perpendicular than this case when, of course we wanted to call this thing y, right? Because we were looking at x and y. Well, in this case we would say maybe this is x, and then we would say that less perpendicular means that y is kind of not exactly perpendicular to x. So there's some part of y in the direction of x. This should kind of remind you of what we did in the dot product. We'll talk about the connection to that later. And then not at all perpendicular. So we would call that zero measurement, perhaps. Happens when x and y really are in the same direction, right? So if they both start here, yeah, you would hope that we have some measurement to capture this information, right? And I'll zoom out here. So you would want, in whatever measurement you have, you would want the biggest value of your measurement output to happen when they are exactly perpendicular. If they're between perpendicular and parallel, you would want some lesser measurement in between, and then you would want a zero measurement for perpendicularity when they are exactly lined with each other, right? When they're parallel. Notice this is the exact opposite of what's happening in the dot product, right? In the dot product, we go the opposite. We have least parallel up here, somewhat more parallel when one part is in the other, and then we have a ton parallel when they're in the same direction. And we want the biggest value of the dot product to happen there, right? Largest magnitude anyways. So the dot product would be 0 up here, largest down here, some cosine factor in between. With this in mind, let's develop a way to quantify the cross product so that these type of measurements come out. Largest value comes when it's perpendicular, 0 value comes when it's parallel, and then there's some in between values as the angle goes from 0 to 90. In the next video, we will do exactly this. See you there.